Today, we will be talking on refractory materials. Refractory materials are very crucial for all processes which employ heat the material below or above the melting point. In most of the industries, in particular iron and steel industry, cement industry, glass industry, ceramic processing, and I can name few more, the various unit processes are in fact thermally driven. A very high temperature is required in order to convert the raw material into product. So, let us see some of the unit processes. I will not go into the detail of the unit processes because that is not the subject matter of the lecture, but only to appreciate you the fact that the unit processes which are used, for example, in metal extraction industry with which we are concerned, what is the environment under which the reactants are converted into products, so that you can appreciate the requirement of refractory materials. So, let me classify now unit processes. There are two classes of unit processes. One which operate below the melting point of material, below the melting point of materials, and other class of processes they operate above the melting point of materials. The melting point of materials. Now, let us further classify both of them. First, I will take below the melting point of materials. So, below the melting point, I am writing short form of melting point. Below the melting point, the processes are, that means below the melting point, you do not heat the material above the melting point. The processes, one of the processes all of you know is the reduction of oxides. Reduction of oxides. These processes all of you are aware for the production of sponge iron. Now, in these processes, temperature is approximately in the range 800 to 1000 degrees Celsius. That is important for us to know the environment in which the reactants are converted into product, and then we have to search the material which can sustain the environmental effect of the various phases which are formed during conversion of raw material into product. So, the temperature is one, and the phases which are present, phases which are formed also at that temperature. Of course, one is the solid phase, then you have gaseous phase, then you have gaseous phase, and among the gaseous phase you have CO2, CO, nitrogen, and if H2 is used, then hydrogen and H2O. These are the gases which are present. Now, if I take another example, for if we take roasting is another unit process which is carried out below the melting point of each component of the reactants. That means, we do not heat the material or the reactants above the melting point. So, here again the temperature is of the order of let me say 900 degrees Celsius, the phases which are present solid at 900, then you have gaseous phase, and here gaseous phase could be SO2 in addition to CO or CO2 or nitrogen. Roasting is a very typical unit process which is employed for the extraction of metal from sulfides. Another unit process is calcination. Calcination. Now, in calcination, for example, calcium carbonate, which is used in the cement industry, there calcium carbonate is decomposed into calcium oxide and CO2, and again the temperature requirement is very excessive. So, I can quote two examples. One is the cement industry, where temperature is of the order of 1200 to 1250 degrees Celsius or even 1300 degrees Celsius for the decomposition of calcium carbonate. Then in say aluminum industry, where the alumina which is produced by the Bayer's process is subjected to very high temperature for drying, because the requirement is to have anhydrous alumina for electrolysis. So, here also the temperature is of the requirement of the 1300 degrees Celsius. That means, very high temperature is required for the calcination, for example, in cement industry or in aluminum industry. Now, here again the phases are solid and gaseous phase. Then you have further deformation processing. Deformation processing. Now, in all finished product operation, for example, in the steel industry, the bloom, slab or billet, they are heated to 1200 to 1250 degrees Celsius in order to perform the deformation, say by rolling, by extrusion, by sheet metal working, by forging or whatever. So, here again these blooms, billets or slabs, they are heated to a high temperature, of course below the melting point, for deformation processing. So, here again the temperature requirement is of the order of say 1200 and in some cases 1250 degrees Celsius. The phases which are there, again solid phase and you have gaseous phase at high temperature, and gaseous phase is at high temperature. Still another operation, see all of you know, is the heat treatment. Heat treatment. Now, here again the high temperature is used, of course below the melting point of the steel, in order to perform the various heat treatment operation like annealing, quenching, normalizing and so on. So, here again the material is heated up to 900 to 1000 degrees Celsius depending on the composition. So, here again the temperature requirement, let us put it around 900 to 950 degrees Celsius. In some of the annealing treatment which is carried out at high temperature, the treatment is done under gaseous atmosphere. So, we have the phases which are there in some heat treating operation. Solid phase is one, then we have gaseous phase like CO, if there is a reducing atmosphere is required. CO2, if you have oxidizing atmosphere is required, then nitrogen if you require an inert atmosphere. Still another processing operation is sintering. In sintering also the material is heated below the melting point, but at a very high temperature depending on the material. For example, if you are doing sintering of ceramic, then you go to a temperature of 13, 14 or even higher temperature than that. So, here the temperature could be around 1200 or even to 1300 degrees Celsius. The phases again solid and gaseous phase. So, from this classification of various unit processes which are used below the melting point, what message I have to give you is very simple. When you perform this high temperature operation, then the phases which are present, first of all, they are very important in order to find out a suitable material, so that these reactants can be processed. Now, these are the processes for below the melting point. Now, let us look at some of the processes above the melting point. Above the melting point of materials, one process, smelting. You heat above the melting point to carry out separation between the phases, for example, slag and metal. So, there are two types of smelting. One, you have the matte smelting, and another you have reduction smelting. Now, in both these matte smelting or reduction smelting operation, the temperature is very high. For example, in matte smelting, if we take, which is used for production of copper, the phases which are in contact with the reactor or what you are going to design, these phases are liquid matte, which is a composition of Cu2s plus FeS, and the temperature is of the order of 1400 degrees Celsius. Mind you, it is a liquid matte, and liquid molten salts are very reactive, and you require altogether different choice of material. In case of reduction smelting, the typical example is that of blast furnace and imperial smelting furnace for production of zinc. They are the typical metal extraction processes employing the concept of reduction smelting. So, if you go for, say, blast furnace, for example, reduction smelting, the blast furnace, the phase which is there is hot metal. The temperature is of the order of 1300 degrees Celsius, or I am giving just approximate temperature. Then the phase which is formed is also slag, is a phase, is also at temperature 1300 to 1400 degrees Celsius. Then you have gaseous phase, which is CO, CO2, H2, H2O and nitrogen. These are the phases which are in contact with the walls of the reaction chamber which you are going to design. In case of matte smelting, the phase is liquid matte, also the phase is slag. Slag is a mixture of oxides, sulfides. Mainly it is a mixture of oxides, that is also at the same temperature or little higher than the matte temperature. Now, in case of, say, imperial smelting process, which all of you know, imperial smelting process which is used to extract zinc, the phases which are in contact with the walls of the reaction chamber, zinc vapor. Mind you, zinc vapors are very reactive, so you have to search accordingly the material. Then the phase which is in contact, the gaseous phase CO, CO2, then you have lead and you have slag. What I wanted you to appreciate is to see that these are the type of phases with which the metal extraction industry have to deal with in order to find a suitable material for the reaction chamber. Another, say, unit process for this in this class is converting. Now, in converting, the phase which is in contact is simply mat. 1300 degrees Celsius or even to 1400 degrees Celsius, then the gases will form. Gas will be SO2, N2, so on. Also at the same temperature, speed of the gases is important, velocity of the gases is important, turbulent flow of the gases is important. So, these are the important issue, say for example, in a unit process which is used for converting, and this converting is typically used in case of extraction of copper. Third example of this one is the refining. In steel making, refining is done to produce steel from hot metal, and for example, refining, say in case of steel, the phases which are in contact, phases are say liquid steel, liquid slag, and gases. They are at around at temperature of the order of 1600 to 1700 degrees Celsius under a very diversified conditions in which these phases are there during production of steel from hot metal. All of you know the process like LD converter or electric furnace steel making. Then there are certain unit operations, processes or operation which are used for simple melting. For example, aluminum, we just want to melt and cast it. So, here you heat the material above the melting point of the material. If it is say aluminum, you go around 750 at degrees Celsius, or if it is copper, you go around 1100 or 1200 degrees Celsius. So, you go above the melting point, so that you can cast these materials for to get a particular shape. So, what we can learn from here, when we want to infuse this idea into the refractory material, then the following facts emerge. You have to see what phases are in contact. So, the phases which are in contact in all unit processes that I have discussed, could be many more in other industries also. For example, in glass making industry, you have glass in contact with the walls of the refractory chamber. Could be another industry where high temperature phases are involved, temperature is involved. You can make the list complete. So, the phases which are in contact, one is the slag, and slag is a mixture of oxides, the mixture of oxides. You have molten metal or say molten steel, which has iron, carbon, silicon, sulfur, phosphorus, nitrogen, oxygen, hydrogen. These are the phases which are present in molten steel. So, gases, and these gases could be CO2, SO2, SO3, nitrogen, carbon monoxide, and etc. The important thing in case of gases, they are moving, say speed of movement is also an important issue. Gases will be in contact with the reaction chamber, that is also an important issue. The movement is highly turbulent. Also, molten steel, there is a continuous motion in case of slag and steel while producing steel from hot metal. The turbulent motion, the reactivity, and all these are the important issue in case of the phases which are present. Of course, solid phase is also a phase over there. But solid phase may not be that reactive in the sense as compared to liquid and gases. So, given this scenario before us, there are different phases at different temperatures. Their state of movement is also different. In some processes, the phases are laminar flow, in some phases are in turbulent flow. Also, it is important the phases are in contact for different time intervals. For example, in roasting typically it may take 1.5 to 2 hours. Converting may take, say, from matte to copper, it may take around 2 hours to 3 hours. Steel making, while converting hot metal to steel, typically LD steel making takes an hour. Electric arc furnace, it may take around 1.5 to 2 hours. So, what I wanted to say is that besides the temperature and the phases, also important issue is the time during which the phases will be in contact with reaction chamber. So, these are the important issues which we have to think while searching the refractory material. So, now what we in fact need? What we need? If I want to summarize, we need, to my mind it comes, we need two things. Some of the processes are autogenous. You do not supply any heat from outside. For example, in steel making, LD steel making, it is autogenous. Roasting, it is autogenous. Also, in case of processes where you supply heat from outside, say you are heating your reaction chamber by the use of fossil fuel. So, you want to conserve the heat. In case of autogenous processes, you want to utilize the heat which is produced during the reaction such that you do not need to supply any heat from the outside, and still you can get the output in terms of temperature, quality, quantity as per you have desired. So, one important thing that we are looking is to minimize heat losses. To minimize heat losses. Typically, this is important. Higher is the heat losses, more calorie you are losing it, and if the process is autogenous, you may end up in the problem. You may require to supply heat from outside. If you are using externally fuel, you have to supply more amount of fuel. So, in fact, it directly relates to conservation of energy. Second important thing is that to allow thermal energy dependent, conversion of reactants into products. Now, what this thing means? Given to us, these are the phases. We can look the periodic table and we can find out that particular metal which can sustain a very high temperature. Can we use it? No, definitely not, because the metallic material, if it is used, it will not meet the two requirements which I have just now listed. The phases will be highly reactive and you cannot do anything out of the metallic material, though they are available to sustain high temperature. Now, the question comes, what are available to us? What is available to us? What is available to us? That is where we call them refractory materials. Now, the term Refractory means anything which can sustain a high temperature. A high temperature normally here in case of metal extraction, it means that that material should not fuse at the temperature of operation. So, all those materials, whether it is metallic material or non-metallic material, they will be classed as a refractory material. But considering the application of those materials for the purpose which I have listed, or in order to handle the phases which I have just now listed, metallic material, because of the cost, because of the higher thermal conductivity, they are out of question. They cannot be used at all to construct a reaction chamber. So, what we are left with, the refractory materials, which are the two types. One, oxidic, and another is the spatial material. Now, among oxidic, they are oxides. What we are talking about, the refractory material, they are oxides. So, then you have acidic, and in the acidic refractory material, SiO2 is the main component. Its melting point is around 1720 or 1730 degrees Celsius, very high melting point. The typical examples, say fire clay is one, quartz, silica, ganister. Fire clay is a mixture of alumina and SiO2, where in the fire clay the alumina content is around 30 to 40%. Of course, this acidic refractory material, which have main component as SiO2, they cannot be used in an environment where you have basic oxides. Now, here it is important to understand, when I wrote slag as an important phase, then slag is also a mixture of oxides of SiO2, MgO, CaO, Al2O3, CaF2 and so on and so forth. The refractory material which are acidic in nature, they are also having the composition SiO2 and so on. So, the acidic refractory material, in which SiO2 is the principal component, they cannot be used under basic environment, that is CaO, MgO, FeO, they are basic oxides. What will happen? They will react, material will fall, collapse, and the whole thing is lost. So, these acidic materials, they can be used only under acidic environment. Another class of this oxidic is the basic. Into the basic, the typically examples are, say, magnesite, dolomite, MgOC, and also there are other basic refractories are available. Now, here MgO, it has a very high melting point, say of the order of 2650 degrees Celsius. Calcium oxide is also has a very high melting point. So, these are the typically basic refractories. Now, as you know also, this basic oxidic refractory material can be used only under basic environment. If they are used under acidic environment, a reaction will be there and reaction chamber will collapse. Now, the third important class of oxidic refractory is the neutral refractory. Under the neutral, you have chromite, you have carbon, and could be many more. They can be used under acidic or basic environment. So, that is the important point in case of oxidic refractory. Now, another class is the special refractory, and in the special refractory they are used for special purposes. For example, one, we have silicon carbide refractory, then we have cermets, the mixture of ceramic and metal. Another important is the Cylon, also a very important refractory. Now, if you look, say, silicon carbide refractory. Now, the silicon carbide refractory, their carbon content is greater than 85%. Their properties, high thermal conductivity, and high refractoriness, that means they can be used at a very high temperature. They decomposes at around 2200 degrees Celsius and does not melt. They also have, they are lightweight. Then your construction will not be that heavy. They have excellent mechanical properties, Then high thermal spalling resistance, a very good refractory, high thermal spalling resistance, but they are very, very expensive refractory in order to manufacture. Another important refractory in this class is, say, Cylon. This is a solid solution of alumina in silicon nitride. How they are made? A mixture of Al2O3 and Si3N2, that is the silicon nitride, is hot pressed at 18 to 30 megapascal pressure and sintered at around 1700 to 1760 degrees Celsius in graphite mold in order to obtain a low porosity dense product. These refractories have good resistance to oxidation, also resistance to action of molten metals like aluminum, copper, iron, steel and zinc. What I mean, the molten metal, they are very reactive if you require to handle, and there the Cylon refractories, they are very good, but mind you, they are very, very expensive refractory and their production method is also very, very complicated, and you require to produce under a very good environment. First of all, you require a hot pressing of the mixture and you require very pure alumina and pure Si3N2. So, the cost is very high. Of course, due to the economic consideration, the Siloam refractories cannot be used for large applications. Also, another important property, the Siloam refractories are not affected, they are not affected by H2SO4, HCl, borax or all other these things, they do not attack, or they are having good resistance against these particular acids. Another, say, the Cermets. It is a combination of a metal or an alloy and non-metal. For example, an oxide, carbide, nitride and boride. That means you mix metal and these oxides, and the material which you get is Cermet is again for a very important application, because all of you know carbides, nitride and oxide, they are non-conducting. So, wherever those applications of conductivity is important, their Cermets can be used, otherwise they can also be used. So, properties, some of the properties of the Cermets. They have low thermal shock resistance, and high strength at high temperature, high temperature. This is one particular property. They are produced by processing of powders, of ceramic plus metal. So, again the production method is the processing of powder, that is the one of the important method, and these Cermet refractories, they are again very hard and strong refractory. Now, let us see some of the important class of oxide refractories. One, let us take it first of all, fire clay. They contain, first of all, fire clay is a mixture of SiO2 and Al2O3, contains a 25 to 45% Al2O3 and 50 to 80% SiO2. Al2O3 has a very high melting point, SiO2 lower melting point. The addition of alumina, it increases the melting point of the product that you are making by a mixture of SiO2 and Al2O3. Some of the properties, the porosity, it varies from 8 to 24% depending on firing temperature, because one of the important thing that I must tell you is that these refractory materials, whether oxidic or special, they are not naturally occurring product. They are being made synthetically by taking the respective components. For example, if you want to produce fire clay, do not think that fire clay is occurring in the nature, you just dig from the mine and use it. No, it is not there. You have to make SiO2, you have to produce Al2O3, you have to mix them, you have to fire them at very high temperature. It is in this process the porosity gets eliminated or it remains, that depends on the firing temperature and time. That is what a wide range of porosity is there, 8 to 24%. Now, at high temperature, fire clay refractory combine with alkali such as soda and potash. What does it mean? That means in the environment where alkali oxides are there, you should not use fire clay refractory because they will react and the material will collapse. As such, here itself you have the three different classes depending upon the alumina content. You have, say, medium duty refractory, medium duty fire clay, which has 30 to 32% alumina. Then you have high duty, which has 38 to 40% alumina, and you have super duty, which has 42 to 45% alumina. And among these fire clay refractories, super duty refractory, they are again used for very special applications. They are very good refractory. Their typically uses are furnaces, regenerators, ovens and kilns. In most of the processes which handle the material below the melting point, depending on the requirement, fire clay is very widely used refractory among these class. Another important class in this high alumina refractory. Typically, sillimanite, which has around 61% alumina. Then you have mullite, which has 70 to 85% alumina. Then of course, you have pure alumina, which is again a very special type of refractory, can sustain very high temperature. Some of the properties, they have high refractoriness, better resistance to slag, and higher load bearing capacity. You should also know that alumina, it acts as an acid refractory in a basic environment and a basic refractory in a acidic environment. So, that is what another typical property of the alumina. The fusion point is around 1850 degrees Celsius. Of course, you can see in the phase diagram of the different phases corresponding to mullite or selimanite, the melting point. The typically uses of these refractories: blast furnace stoves, cement and rotary kilns, electric arc furnace roof, glass making furnaces also, ladles also, they are being used. Another important class is chromite magnesite refractory. Chromite magnesite refractory. Now, here the amount of chrome ore is greater than magnesite. They can be used up to 1700 degrees Celsius. They are resistant to thermal shocks. And they are basic in nature. What does it mean? If it is basic in nature, you cannot use under acidic environment. And typically they are used inner lining of BOF, and side walls of soaking pits. The soaking pits are typically furnaces which are used for heating a material below the melting point. Then another class is magnesite chrome refractory. Now, here you have MgO content is greater, and this magnesite, dolomite, magnesite chrome, they are all basic refractories. And among magnesite refractory, it has a high refractoriness, and thermal conductivity. Great resistance to basic slag, and they are in fact cannot be used in the acidic environment. There are many other products which are there for very special applications. I have given you some so that you can appreciate what is available to us in order to meet the requirement of the various phases which are produced during conversion of reactant into the product through various unit processes. Now, the choice of refractory depends on what? Choice of refractory depends on what? Choice in fact depends on several factors. You have seen there are various types of refractories are available. Various can be produced by this combination of SiO2, Al2O3 or MgO, Cr2O3, carbon and so on. The choice depends on one of the important factor is the furnace design. Furnace design is one of the important factor, and among furnace design, what is meant over here, what is the condition of heating? Condition of heating. Under condition of heating, whether once you have heated, does it remain for months together? For example, a coke oven, when it is heated once and brought to a temperature 1200 degrees Celsius, it is left for years. Then the refractory requirement, or a cupola, which is every day it is heated. So, these are the things which are important in case of furnace design. That is, what is the requirement of the treatment of reactants and how long a furnace should be kept under the hot conditions, and accordingly the selection of refractory has to be made. Another important criteria of a furnace design is the loading. Say, how are you going to load and how much is the load that the refractory has to accept it. And third important thing is the degree of insulation. Degree of insulation. Could be one or two factors more. That means you have to decide what type of furnace you are going to design for what particular operation. Accordingly, you have to select the material. Another important choice that depends upon the so called operation. Now, under the operation, what you should know? Chemistry of phases, what phases are present, solid, liquid, gas, metal, vapor and so on. What is the temperature? And you have to go for the maximum temperature. What is the fluidity of phases? Fluidity of phases. And also it is important to know abrasion during movement. Abrasion due to movement. So, these combination of furnace design and operation will tell you what type of refractory material you should use it. You may go for a very high quality, it may not be required, though it is good, but from economic consideration may not be required. What I mean to say, the selection of refractory is very complicated and one has to understand the unit process very well in order to optimally design with the refractory material and to create a reaction chamber which can sustain the diversified requirement of the phases and to give a longer life. Because ultimately, it is the life of the refractory that is more important. Life of the reaction chamber that you have designed is the more important. On that account, there are certain properties which we have to look, and we will see this in the next lecture.